So here's chapter 4. We're going to go through it rather quickly and then use supplemental videos to help solidify the particular applications that we'll be using. So for chapter 4, it's fluid kinematics. So I want you to think of kinetic energy and how that is the motion of something, right? So you have potential energy. You can kind of think of that as the stored motion. And then the kinetic energy is that change in location over a given time, point A to point B. And so that's the same overall arching feel here, just in regard to fluid or fluid flow. Here's the CFD interpretation of a hurricane off the coast of Florida. And so you can just see that each little particle is digitized in a CFD analysis, which is computational fluid dynamics. And so here it gives you the overall pattern of this hurricane. And so one interesting thing is right here is the wall, or approximately the eye wall, which is within the wall is this point of stagnation. This area is very calm. It's not moving. It's not changing. There's nothing really going on. But this eye wall right here, which makes hurricanes so dangerous and so violent, is this extreme rotational behavior that occurs at this eye wall. And then everything else around it is irrotational. So it's just the core that is the rotational. But the most amount of damage happens on this eye wall. And then everything else flows from that in an irrotational pattern. Here's the objectives. Again, we're just going to go through these slides pretty quickly because you have them. So kinematics is a study of motion, just like kinetic energy. And then when we talk that on a fluid basis, we've got the study of how fluids flow and how to describe the fluid motion. We can do that through a couple of different ways: CFD, computational fluid dynamics, and then you can do some experimental approaches. Of course, we have a math language that we love to use here, and there's multiple different ways that we can do it, but we're looking at the motion of the fluid. There are two different ways to describe this motion, and that's the Lagrangian and then the Eulerian. So the Lagrangian description is the path of an individual object, right? So it requires us to track the position and velocity of each individual fluid particle and to take that from like a starting point to an ending point. And so to track that individual particle. Over here on the right, you can see particle A, B, and C. And you can see how they go from point A to point B using a vector of direction. That's very difficult. It's something that we don't do often. It's not used widely, but you can see that this effect would be absolutely usable if you were playing pool. You know, there's only 2, 4, 6 balls there, or a weather balloon, something like that, something that you can see that you would need to look at the path, that fluid path of just that one item, right? And so that's when we would use the Lagrangian description. Otherwise, we're using the Eulerian description. And that's when we start looking at a flow domain or a control volume. We're defining that control volume of flowing in and out of an area, right? So we are defining that control volume, and then we're looking at the field variables within that over space and time, okay? And so some of the ones that we look at is pressure field, scalar field, variable velocity, vector, so all of those in here. And that's our flow field, right? So we're not concerned about the actual particles within the flow. We don't care about that. We don't care if it's particle 1 or particle 1 million. We're just concerned about the control volume and what flows in and out of that. And that's what we're looking at. Here in the Eulerian description, again, we don't really care what happens to the individual particles because we're looking at the process or the volume as a whole, that control volume, okay? Here at the bottom, you can see a description. So in the Eulerian description, we define field variables such as the pressure field and the velocity field at any location in an instant in time. Okay, for example, the airspeed probe mounted under the wing of an airplane measures the airspeed at that location, right? So we're not concerned about every single little particle in the air, right? We are more interested in what we can derive from these computations, right? The airspeed, velocity field, pressure field, things like that. And so we do that in relation to a control volume, a specific area that we are looking at, and the flows that come in and out of it. Moving on to a velocity field. This is a steady two-dimensional velocity field. You can see that denoted because we are on an XY plane, and we have a scale here of 10 meters per second. And so here it just says, it just lets you know that what we're looking at, I'm making some notes on here, but I guess they saved. So what we're looking at here between these two is this control field, right? And just to let you know, these black curves, the solid black curves, represent the approximate shapes of the streamlines. So we have 4 different kind of lines or flows that we look at. The first one that we look at is streamlines. And unlike the other 3 that we will get to soon, streamlines are the ones that are done in an instantaneous moment. We can look at them instantaneously, whereas the other 3 that we will get to are in overtime, like a displacement overtime. Okay, and so here we can also use them as a math product, so we can calculate them, versus the other ones that are much more derived during experimental, whether we're in a wind tunnel or something like that. That's experimental data, versus this is calculated and then we can model it. The stagnation point is indicated in the blue circle, so that's right here in the middle. So remember this stagnation point, that's an area, stagnation means that there's no flow or no motion. So I want you to think of, remember we looked at the hurricane and we looked at the eye, right? So remember the eye wall, extremely dangerous. That's where all that rotation happens. But inside of it, it's stagnant. There's nothing happening, no motion, no rotation, nothing, okay? And then the shaded region represents a portion of the flow field that can approximate flow into the inlet. We also have an acceleration field, and the equations of motion for fluid flow, such as Newton's second law, are written for the fluid particle, which we also call the material particle. And that's because we take this Newton's second law, which is force equals mass times acceleration, and we just put that on a particle level. But remember, we're not really looking at it on a particle level, okay? Even when we're looking at the Lagrangian description, we're really going to use that to follow an item, right? Like a balloon that's filled with a gas, right? Or a weather balloon. Or we're going to be looking like the example that was given before, a cue ball, right? You're going to be looking at something and following that specific item. We in this class are not going to be looking at it on a particle level. However, it is important to understand how it works because we can apply the Lagrangian description to an actual item. And so here you can see the acceleration of a fluid particle, or maybe the acceleration of, a gas-filled balloon. And so here, Newton's second law is applied to a fluid particle. The acceleration vector, which is this purple arrow here, is in the same direction as the force, right? So if you think of a ball, if you push a ball, if you apply that force to a ball, then it is going to accelerate in the same direction. But the velocity vector, which is this blue arrow right over here, may act in a different direction. Whoops. Okay, here's additional formulas to go with that, which is the acceleration of the fluid particle expressed as a field variable. We have the local acceleration, and then the adjective, which is being defined, and then the gradient or del operation. And so here, Below here on the right is the components of the acceleration vector in the Cartesian coordinates. This is something that's really easy that we will be employing. And so this is on a three-dimensional plane. So we normally see it on an X and Y plane. And so here we have the X and the Y, but you can see here that third dimension for the Z. And so while we'll have it, we will typically display it on a two-dimensional plane. And then here you can see that the fluid particle at a time when it started off versus the change in time. And so here this dx, this is the change. If we have the particle right here, right, if this particle is right here, and then we have this particle right here at a different time, then you would have, actually, I drew those equal. Let's do it down here. So you have this one here. And so here you would have this change in x, this dx, and then you would have this change in y as a change in y. And so for here, we have flow through a nozzle. And what this is illustrating is that even if you have a steady flow, even if you have something with the same amount of force through it, the same amount of input versus output, everything is the same of what you are putting into it, just because of maybe the geometry of the device that you're using or the position, this, up and bend situation, that even in a steady flow, the exit speed of the water is much higher than the input. And so it's saying that fluid particles have accelerated even though the fluid flow is steady. And so here's this nozzle. We actually use this nozzle. It's a device that is used to speed up items just because of its converging geometry, it being smaller here versus bigger here. You can see this again on this is an XQ, and so you have the change in X from when a particle starts here versus ending here. And remember, we're not looking at the actual individual particle, even though it does say particle, right? We're looking at a control volume and what's flowing in it. We don't care about which particle this is. If all of the particles had a name, we don't care that it's particle 37, right? We just care that it is a particle and that it is flowing in and it is flowing out. And so the material derivative, this is how we are going to take the Eulerian framework and apply it to a control volume. So if you have this system, right, if you have this system and then you have this control volume, so say you're looking at, a balloon, right, and it's flowing through this control volume, right? Our system's going through the control volume, and the control volume is what we're looking at also, right? Then the way that we do that, we haven't gotten to it yet, but we will. It's RTT. And what this is Reynolds transport theorem, or I'll just put theory. Okay, and so what this does is this material derivative is shown as d, here you go, d over dt. And what that is that's the rate of change in a property in a fixed mass system. So this is how we are kind of painting it or using this Eulerian framework to solve this system going through a control volume. And this is part of Reynolds transport theory. And so when we have d over dt, which is the rate of change in a property in a fixed mass system, this is the material derivative. Whoop. Looks like I'm getting too close to the edge. Oh no, let's see. Yeah, it's just not gonna let me, not gonna let me go down there. Okay, let me write at the top of it. So this is the material derivative. Okay, and then what that is equal to is we have this little symbol right here. Okay, and what this is called the local term. And what this local term is it's the rate of change of that property, right? So the material derivative is the rate of change in a property in a fixed mass system. And then the local term is the time rate of change of that property inside the control volume. So we're looking at that property inside the control volume plus, we've got a velocity vector. Okay, and then this is the ejective term. And what that is that is the net flux of that velocity of that property through the control surfaces. Okay, so we have first the material derivative, the rate of change in a property in a fixed mass system. Okay, so just the rate of change in that property, that's what we're looking at. And then to get that, we need to look at the time rate of change of that property inside the control volume. And then we need to add that to the net flux of the property through the control surfaces. So it's obtaining that on like a time basis, right, over a period of time within that control volume. And that's how we can take this system and push it through a control volume by way of RTT. Okay, and so here you can see the material derivative. Just a little note right here. It's assigned this special notation that we talked about in order to emphasize that it is formed by a fluid particle flowing through a flow field. So we're following this through that flow field, through that control volume, right? And this system right here, that's our particle, right? And then here we do have some other names. We've got total particle, Lagrangian, Eulerian, and then substantial derivative. But aside from, everything else on the page, something that's really interesting is you can see here that you've got this flow path over here, and it's on this blue line. But when you start out here, you've got this particle at a distance t. And so the difference between this particle at the same velocity and this one change in time is less than the same velocity over the same time, right? We're covering more distance. There's more displacement given it's moving at the, it has the same force. I won't say velocity, it has the same force and it has the same time, but it's increasing in acceleration, right? It's covering more distance. And then here again, we have the same force acting on it and we have the same time change, but the particle is accelerating. So here again, we've got the material derivative, we've got the material acceleration, and then the material derivative of pressure. And then here it just says it's composed of local or unsteady part of the convective or ejective part. And so we talked about these, we just defined them, what this local and then adjective portion is. And so here's a steady velocity field, and this is the material acceleration. Here again, we're just looking at the solid black curves to represent, so we have solid black curves that represent the approximate shapes of the streamline. That's because we can mathematically calculate these. We can put these into a CFD analysis and never even experiment this, right? Because one of the four lines is streamlines, and we can do that not only instantaneous, but we can do that without experimenting. Okay, and then you can see here in the middle is the stagnation point. So we've talked about that, computational fluid dynamics, CFD. This is for flow visualization. We can use this to give approximate or analytical results in lieu of numerical solutions, but we typically do use numerical solutions, right? And then we more than not use a combined effort of both, right? So if we have some information. We have the numerical solution. We will put that into a CFD analysis, and then we will simulate what that flow looks like. And you can look and you can see the streamlines here. They are instantaneous, right? And they're much more stable here at the top. And then you've got some turbulent flow here. And we know that that turbulent flow here is what you can see from this turbulent flow is that this baseball is actually spinning. Because if it wasn't spinning, if it was just stationary, well, then the flow would look more like that, right? It would just be passing across it. But we've got some turbulent, it's throwing it all around. It's the wake of the ball. And so here we've talked about the streamline. This is the curve that is everywhere tangent to the instantaneous local velocity. So an important one is that it's instantaneous. It's the only one that's instantaneous. Okay. And so here you can see the streamline here in the middle, and this can be calculated mathematically. And then from there you can get, you see it's on a two-dimensional plane, you can get things like, here's this point, starting point X and Y, and then you have this, not ending point, but the point at which you are not calculating anymore. And so you have a change in X, and you have a change in Y, and then this dr here is the arc length, so you're able to calculate that. Here's just equation of a streamline and the streamline on an XY plane. And what this is doing is it's just saying, hey, this is how we can get these formulas, but this is what the formulas are. This is what we're concerned about. You can come back to this if you want to know the background of the kind of birth of these formulas. So here again is streamlines and steady, incompressible, two-dimensional velocity field. And so here you see again, it's black lines, solid black curves for the streamlines, and those are calculated mathematically. And then for the velocity field, the blue areas are superimposed for comparison. Okay, so that's the velocity vectors. And so here, this is a really good note. I'll read the whole thing. The agreement is excellent in the sense that the velocity vectors point everywhere tangent to the streamlines. But note that speed cannot be determined directly from the streamlines alone, right? So streamlines, I want you to think of as a path, right? So let's go back to this real one. Can you tell me by looking at this, can you approximate what the velocity of that is? Absolutely not. It's a streamline. It's a line. But you can tell me the behavior of this air, of these particles. You can also look at the streamlines and how they are disrupted, like we did, and we can say, whoa, there's some movement going on here because look at the wake that's behind that. Right? There's a lot of things going on. This is not steady at all. So this is moving. We can tell a lot by this instantaneous shot. But we definitely cannot use it to only determine the speed, right? We need other things. So a stream tube consists of a bundle of streamlines, much like a communication cable, okay? So here it's just a tube and it's a bunch of streamlines. That's what we're looking at. Fluid within a stream tube must remain there and cannot cross the boundary of the stream tube. Okay, so it cannot, here's the boundaries. It cannot cross. The mass needs to stay in there. Okay? And the reason why is it is this little paragraph right here. Since streamlines are everywhere parallel to the local velocity, fluid cannot cross the streamline. So you see it's all running parallel. It can't run tangent. You can't have exit and inlets. It is the tube. And you see that the tube is ill-shaped, right? It's not a uniform shape. So if you think, well, not everything's going to be tangent like this, well, that's fine. But it's not like this, you know? So if it's like this, then maybe your tube just looks like that, right? And then maybe everything's inside of it like this. Right, those streamlines. But you don't have something coming in, you know, like this, or exiting like that. And remember that streamlines and thus stream tubes are instantaneous quantities. They happen in an instant, right? Defined at a particular instant in time according to the velocity field at that instant. Here you have the stream tube consisting of a bundle of individual streams, and then down here you have A and B, which is just converging and diverging. And then you have, so this could be a nozzle. You could think of this as a nozzle. This is the shape of a nozzle anyway. And then this diffuser, right? And so this, the acceleration increases, and then here the acceleration or velocity decreases. In an incompressible flow field, a stream tube A decreases in diameter as the flow accelerates, right? Or converges. And B increases in diameter as the flow decelerates or diverges. So when you have two, just a fun fact, when you have two, this is what I did my thesis on, which honestly is not that very interesting. I mean, it was interesting for me, but I understand it's not going to be interesting for almost anyone else. I did do the flow of particles at supersonic speeds in a converging, diverging nozzle, and it's called a de Laval nozzle. So what it does is we accelerated it, and then at the cross-sectional area in the middle, we hit supersonic, and then it came out. And then to, so you can imagine if you have some particles coming in, and then coming out, it's just going to go everywhere, right? So what we did is we put just a little bitty converging nozzle on the edge, again, to just kind of push all the particles to a particular point. Fun fact. So path lines, what is a path line? It's the actual path traveled by an individual fluid particle over the same period of time. Okay, so it's just a path line, right? A path line is a Lagrangian concept, in that we simplify flow of a path of an individual fluid particle as it moves around the flow field. Or if you had a balloon in the sky, this would be the path that it was taking. Okay, and so you see this path in a vector, an x, y, and z vector in regard to particle at some given time. Okay, and so that's the material position vector. Here, path lines produced by white tracer particles. So sometimes we'll use tracer particles, and we'll follow particular tracer particles, suspended in water and captured by time exposure photography. That's because we need like long exposures, right, to be able to capture something that is happening over time, because we can't see it with the naked eye. As waves pass horizontally, each particle moves in an elliptical path during one wave period. And so you can see these wave periods. We've got a wave period and a wave period. And so we've got some paths here, right? And an elliptical, you can see it. You can almost see the streamlines, right? Not, I know you can't like map a streamline here because that's a mathematical thing, so you're not going to be able to do it, but you can see the pattern of it. So when we're getting into the imagery of these, because this is how we simulate, this is how we're going to look at them, because obviously we cannot see most of these things with a naked eye. We can't see every single water particle, right? We can use particle image velocimetry, PIV. It's a modern experimental technique that utilizes short segments of the particle path lines to measure the velocity field over an entire plane of fluid. So what we're doing is we're using just short segments of the pathways to measure the velocity field over an entire plane of flow. Recent advances also extend the technique to 3 dimensions, and so that way we have this XYZ. And so what we normally do, so in PIV, tiny tracer particles, remember we looked at those tracer particles before. They're suspended in some sort of fluid, and remember that can be liquid or gas. And the fluid is illuminated by 2 flashes of light, so it's heavily dependent on you having the correct light to extrapolate this data. right? And so it can be a light sheet from a laser to produce 2 bright spots, and then it's recorded by a camera for each moving particle, and it would be those tracer particles. Okay? And then we can do both magnitude and direction of the velocity vector, and can be inferred. So we can use that starting to ending over that tire plane to see the movement, the velocity, the behavior of it. Here's stereo PIV measurements at a wingtip vortex in the wake of a NACA 66 airfoil at an angle of attack. So what this is showing is, so the black line denotes the location of the upstream wing trailing and the coordinates normalized by the air coil and the origin of the wing root. But here we have the vectors denote fluid motion in a plane of measurement. So you can just see all it's doing is it's just showing you the path and the fluid motion and how it's working. Oh. And then one here, the color of the map is obviously very substantial, right? So this area you would be able to denote and tie to this portion of the scale, because we do have scales in here. Okay, here we have a formula for the tracer particle location at a time. And this is just in using path lines, right? And then we get into streak lines. So remember, we had streamlines, and that was instantaneous math-driven. Streak line is not math-driven, and it's not instantaneous. It has to be over time. The locus of fluid particles that have passed sequentially through a prescribed point in the flow. So we start here, and then it goes along the streak line. And this is the dye or smoke. It's coming in here with this particle, and then it's going over the streak line. And so it is not instantaneous. It has to be over time, right? Streak lines are the most common flow patterns generated in a physical experiment. Remember, they are not mathematically driven. They are experiment driven. If you insert a small tube into a flow and introduce a continuous stream, in here, dye or smoke, of tracer fluid, dye in a water, smoke, things like that, the observed pattern is the streak line. Okay, and then here again, a streak line is formed by a continuous introduction of dye or smoke in at a point in the flow, and it's labeled tracer particles 1 through 8 were introduced sequentially, and so you can see those along that streak line. Streak lines produced by colored fluid introduced upstream since the flow is steady. These streak lines are the same as streamlines and pathways. So they can be the same in steady flow, right? So streak lines, streamlines, and pathways are identical in steady flow. They can be quite different in unsteady flow. That's very important to know that relationship, right? And so when we have a steady flow, say we have, does it say what this is? No. So this is something here, right? It's an object. Something is right here. And so we have those streamlines, those streak lines, those path lines, things like that. And they're all going to be identical because it's a steady flow. It's just something in the way, right? So if you inject a colored dye, it's going to follow all of those because it's a steady flow. But if you have an unsteady flow, they're going to be all over the place, right? They can be all over. They can be going this way and that way and that way, and they can just be all over the place. Okay, and so here the main difference is that a streamline represents, we've talked about this, streamline represents an instantaneous flow pattern at a given instant in time, while streak line and path lines are flow patterns that have some age and thus a time history associated with them. So you need to have something over time. You need to have motion, right? We're in this chapter of fluid kinematics, right? A streak line is an instantaneous snapshot of a time-integrated flow pattern. So just because you're looking at an instantaneous snapshot does not mean that you're not depending on that time-integrated flow pattern. A path line, on the other hand, is a time-exposed flow path of an individual particle over some time. So streak line is, hey, we're taking a whole picture and we're looking at these particles in some kind of time integrated pattern. And then a path line, you know what we're doing? We're doing a time exposed snapshot where we're going to see this individual particle move and flow over a certain amount of time. So here we talked about Reynolds, right? We talked about Reynolds transport theorem. Okay, and the Reynolds number of the flow is RE equals 93. In the figure, streak lines are introduced from a smoke wire located just downstream of the circular cylinder in a diameter D aligned normal to the plane fluid, because remember, we always align normal to. When multiple streak lines are introduced along a line, as in this figure, we refer to this as rake or streak lines. Okay? So smoke streak lines introduced by a smoke wire at two different locations in the wake of a circular cylinder. So here's the cylinder, and then we have two different streams of smoke, and then look, you can see one, and then you can see the other, kind of like this, if we were to look at it upside down, or the opposite. Okay, and so time integrative natural streak lines is clearly seen by comparing the two graphs. And so you can see here, if we're looking at A, smoke wire just downstream of the cylinder, and then B, smoke wire located, the time integrated. So you can see the difference between two of them. You can see going in and looking at a time integrative nature. Because of the unsteady vortices shed in an alternating pattern of the cylinder, remember we talked about this alternating pattern, the smoke collects into clearly defined periodic patterns called Kármán vortex streak. A similar pattern can be seen at a much larger scale when the airflow in the wake of an island. Okay, so it's just the Kármán vortices when we see these alternating. So here's a page, again, just letting you know the background information about these formulas. And basically, mathematically, the location of the tracer particle that we've been talking about is integrated over time, and it's T inject to the present time TP. And so you see this integral here, this integration. Okay, and then X again is just the location, because we're on an XY axis, so you've got the injection point, and then you've got a change over time with a velocity. And then here you've got the tracer particle location over time. So again, you have the start of it, you have the integration, and then you have the change in velocity and the change over time. So here you have unsteady flows. Remember, we talked about it and we said, hey, when it's a steady flow, all of these lines, these path lines, these streak lines, these stream lines, they're all the same. Because it doesn't matter, it's a steady flow. But when you have an unsteady flow, look at this. It's all over the place. So the stream lines look really good because they're mathematically induced. But when you get to it and you start looking at path lines and streak lines, over time, right? Not an instantaneous look, but over time, then you have this drastic difference where they're just all over the place. Right? Just all over the place. Streak lines and path lines are wavy because of their integrated time history, but the streamlines are not wavy since they represent an instantaneous snapshot of the velocity field. So that is just one snapshot, right? But when you're looking at it over time, you're looking at the path lines, you're looking at actual path lines, right? And so those are going to be wavy, especially in an unsteady field. In a steady field or a steady flow, it'll definitely be all the same because they're going to follow along the same paths. Timeline, a set of adjacent fluid particles that were marked at the same time earlier in an instant. So when you think of timeline, think of developing a timeline, right? And so that can be whatever your timeline needs to be, right? So here is a flow, and you mark a flow here to here, and then you've got another time here to here, and then you have another time here to here, right? And so here, timelines are particularly useful in situations where the uniformity of flow or lack thereof is to be examined. So if you want to look at something being steady versus unsteady and the behavior of these particles, then you can break it up into timelines and then compare those timelines together. Here you can see the velocities changing as we've got some drag along the walls of it. So here, timelines produced by a hydrogen bubble wire are used to visualize the boundary layer velocity profile shape. Flow is from left to right, and the hydrogen bubble wire is located to the left of the field of view. So it's over here. Okay. Bubbles near the wall reveal a flow instability that leads to turbulence. So it is based on the refractive property of light waves, so this is how we visualize it. So when we look at things like this, right, we can base this on the refractive property of light waves. The speed of light through one material may differ somewhat for another material, or even the same material, if the density changes, right? Because if you're trying to go through something even with just light or sound, the density is heavily dependent on how it behaves within that. As this light travels from one fluid to another, with a different index of refraction, the light rays bend, and they are thus refracted. Okay, two primary flow visualization techniques that we use, the shadow graph technique and the Schlieren technique. And looking at the interferometry, it is a visualization of techniques that utilize the related phase change of light as it passes. And so, of course, you have temperature differences that cause density variations, mixing fluids, supersonic flows, things like that. And so those techniques are very useful when we're looking at those natural convection flows. So unlike the flow visualizations involving streak line, path lines, and timelines, the shadow graph and Schlieren methods do not require injection of a visible tracer. And we won't go through all these because we have an example as well. But they show the refractive property of the light. And so then you can see the invisible. And I want you to think of like the heat that just naturally radiates from you. That would be something that is flowing, right? A unusual flow, but it didn't involve some sort of injection, any sort of like tracer, right? It doesn't involve any of that. And so there you can see the invisible. Okay. And here's a Schlieren image of Mach 3 flow from left to right over a sphere. A curved shock wave called a bow shock forms in front of the sphere. So this is the shock wave here. You've got a shock. Oh, that was terrible. I'll just draw an arrow to it. You have a shock wave. So you have a shock wave and curves downstream. And the forwardmost location appears as a thin red band. And then the yellow band of the image. The yellow band is caused by the bow shock wrapping around the sphere. And then the shocks coming off the sphere downstream are due to the boundary layer separation. So this is just showing you the complete shock wave in front. Okay, and so here you can kind of see that visible, right? He's not needing to inject any sort of dye or tracer particles in here. A shadowgram is not a true optical image, but it's merely a shadow. The Schlieren image involved lenses and a knife edge or other cutoff device to block the refracted light as it focuses on the optical image. So it's a heavily modified, heavily tooled optical image using light to be able to see things like this. And so here we have the direction of the fluid flow immediately above the solid surface can be visualized with tufts and that short flexible strings glued to the surface at one end that point in the flow direction. They are especially useful for locating regions in flow separation. right? Where the flow direction suddenly reverse. I always think of this like grass. You that's what I think of. And when the flow direction suddenly reverses in air, you can see that, in your blades of grass if your grass is a little higher. A technique called surface oil visualization can be used in the same purpose. Oil is placed on a surface and forms streaks. So if you have, a table, right, and you have the flow of air, and you have this little ball of oil, well, that's going to blow out, and you have a force coming this way. That's going to blow out the oil here. And then here, regardless of how the results are obtained, analytically, experimentally, or computationally, it's usually necessary to plot the flow data so that it makes sense, so that you can give it a full picture. Okay? And so we talked about time plots, but here, and we also have XY plots. And in this section, we discussed the three additional. We've got profile, vector, and contour plots. So here's a profile plot. It indicates how the value of a scalar property varies along a desired direction. So you have this on a U, Y here. And so we have down here at the bottom, in fluid mechanics, profile plots of any scalar variable, and we're talking pressure, temperature, density, can be created. But the most common one used in this book is the velocity profile plot. And here, profile plots are the horizontal component of the velocity as a function of the vertical distance. So it's that horizontal component of the velocity, but taking into account its vertical distance in a flow, right? In the boundary layer, growing along a horizontal flat plate. Okay, and so A, this is a standard profile plot, and then B, it's a profile plot with arrows. I love the simplicity of that. But here you can see how this is changing, how this flow is getting much more steady. Vector plots is an array of arrows indicating the magnitude and direction over a vector property at an instant time. And so you have those streamlines. Again, we looked at these a little bit earlier. Streamlines indicate the direction of the instantaneous field, right? So we can see the pattern, the way that they are going, but they don't necessarily indicate the magnitude or the speed, right? The velocity. It just gives you the direction, the path, behavior of it. Okay, so a useful flow pattern for both experimental and computational fluid flows is the vector plot. And it has all of those array of arrows. And here, vector plots can be generated from experimental data, PIV measurements numerically from CFD, because remember, when we're looking at streamlines, those are mathematically derived. Here's a CFD calculation of flow impeding on a block. And so you can see this. You can see the symmetry plane. You can see all of these vector arrows. You can see, the behavior of it. It's coming up, and then we have some of that drag force, and we have some coming back around, and then some flowing up. And then as you get way up here, you start getting something a little bit more steady. But this is looking much more turbulent than up here where it's a steady flow. Here's a block with the recirculating eddy in a symmetry plane. So right behind it, we have that recirculating, that drag. Okay. And then a contour plot shows the curves of a constant volume as a scalar property, which is the magnitude of a vector property at an instant in time. Contour plots, also called isocontour plots, are generated from pressure, time, velocity, magnitude, and many others. And so when you have a contour plot that consists simply of curves indicating various levels of the property that you're looking at, that's called the contour line plot. And then you have, on the other side, this contour filled with either colors or shapes, right? Then that's going to be the filled contour plot. Okay, and so we have other kinematic description. So you have types of motion or deformation of fluid elements. We have translation, rotation, linear strain, also called extensional strain, and then shear strain. And so all four of those motions or deformations usually occur simultaneously. So you can have them all at the same time. So it is preferable in fluid dynamics to describe the motion and deformation of fluid elements in terms of rates. And so when we remember, we put a little dot over rate. And you've got velocity, angular velocity, linear shear strain rate, and then shear strain rate. And in order for these deformation rates to be useful in calculation, we must express them in terms of velocity and derivatives of velocity. And so here you can see transitional. This is the body staying the same. It just has a placement change. So if this is an x-axis, you just have a change in x, right? And so rotation is B. The subject is still staying the same. It's just rotating. And so here you will have a change in x and a change in y. And then here you will have linear strain or extensional strain. And so that's when you are taking that square and you're pulling it on each side, like tension. And so that is going to be a change in the x direction. And then when you have shear strain, that means that you're kind of pushing it you're taking it by its corners and pulling it apart is the best way for me to describe it. And here you'll have, again, a change in x and a change in y. You do have the rate of translation vector, and it's described mathematically as a velocity vector. Here's the formula here in a Cartesian coordinate. And the rate of rotation, or the angular velocity at a point, is the average rotation rate of two initially perpendicular lines that intersect at that point. The rate of rotational vector is equal to the angular velocity vector. And when we have linear strain rate, that is the rate of increase in length per unit length. Here's additional information for how we get these formulas that we have. Volumetric strain rate, or bulk strain rate, is the rate of increase of volume of a fluid element per unit volume. So when we have a kinematic property that's defined as a positive when the volume increases, and another synonym for volumetric strain rate is called the rate of volumetric dilation. So the irises in your eye dilate or enlarges when it's exposed to dim light. And just a note here, the volumetric strain rate is 0 in an incompressible flow. And here, what if we have an air parcel? Air being compressed by a piston in a cylinder, the volume of the fluid element in the cylinder decreases, corresponding to a negative rate of volumetric dilation. Shear strain rate, at a point, half of the rate of decrease of the angle between two initially perpendicular lines that intersect at a point. And then here we just have these formulas: shear strain rate tensor for the Cartesian coordinates for both. So here it shows general in its 2D situation in which compressible fluid flow, in which all possible motions of deformation are presented simultaneously. So you have all four of those. You have the translation, rotational, linear strain, and shear strain. Because of the compressible nature of the fluid flow, we know that there's the volumetric strain, or the dilation. I love this. You should now have a better appreciation for the inherent complexity of fluid dynamics. I bet. Here's streamlines again with the stagnation point colored. And deformation of an initially square parcel, right? So here's a square parcel of air, and down through the streamlines and the vectors, it has now deformed. let's end it here and pick up with a lecture to finish the other half.